Hello everyone, my name is Manav Kohli and I am a PhD student in Gil Zussman's group at Columbia University. Today, we will demo our work entitled Remote Experimentation with Open-Access Full-Duplex Wireless in the COSMOS Testbed. First, we will briefly go over the COSMOS Testbed and the concept of full-duplex wireless. Then, we will take a look at the integration of our full-duplex hardware with the COSMOS Testbed. Finally, we can see a demo of the hardware in action. So let us start with the COSMOS Testbed. The COSMOS Testbed is an open-access testbed for wireless communications that is part of the NSF Platforms for Advanced Wireless Research program. COSMOS aims to address the needs of next-generation wireless communications by providing features such as low latencies, high bandwidths, and a real-world city-scale environment for experimentation. COSMOS achieves its goals through the use of cutting-edge technology such as millimeter-wave phased arrays, miles of city-provided dark fiber, and most importantly for this talk, integrations of customized hardware, such as our full-duplex radios. COSMOS will occupy a 1 square mile area in West Harlem, New York City. The testbed area has been designated an FCC Innovation Zone. As we move on to Phase 1 of deployment, the resources deployed in the pilot phase are generally available for researchers to use. The pilot phase includes 2 indoor sandboxes. Sandbox 2, located at Columbia, is where our custom full-duplex radios are integrated and remotely accessible to experimenters. Now, we can have a look at full-duplex and our full-duplex radios. Existing wireless systems are known as half-duplex, meaning that they either separate transmission and reception into different time slots or into different frequency bands. Full duplex wireless systems, on the other hand, allow for simultaneous transmission and reception on the same frequency channel. The benefits of full duplex wireless include an increased throughput at the physical layer, up to 2 times, with lower latency and more flexible use of the available wireless spectrum. One of the main challenges associated with full duplex is what is known as self-interference. For successful full-duplex communication, we must cancel the comparatively much more powerful transmitted signal from the signal that we receive. It can be helpful to regard such a system as analogous to a pair of noise-canceling headphones. Outside noise, which is known to the headphones, is processed in such a way that it can be cancelled from the audio signal. Our self-interference canceller is based on the principle of frequency domain equalization, which is suitable for an integrated implementation. The self-interference channel can be emulated in the frequency domain using reconfigurable bandpass filters with amplitude and phase control. Multiple bandpass filter taps can be used in parallel to increase the cancellation bandwidth. We call this our Generation 2 canceller. We can note that this is analogous to an audio equalizer, which is used to provide a desired profile in the frequency domain. We can now take a look at how we integrate our custom full-duplex radios in the COSMOS testbed. The first step of integration is to emulate the integrated circuit implementation on a PCB. This gives us a more robust interface to the software-defined radio platform. The particular PCB shown at the bottom of this slide also emulates an older Generation 1 narrowband canceller implementing a single tap with amplitude and phase control. We include this PCB along with other components including an antenna tuner, circulator, and sub-20 USB to SPI interface in our Gen 2 canceller box. 2 such boxes are integrated in COSMOS Sandbox 2. The integrated full-duplex radios can achieve over 50 decibels of cancellation across 20 MHz bandwidth in the RF domain, thus enabling wideband full-duplex communication. The topology of Sandbox 2 is shown here. The experimenter may log into the Sandbox 2 console over SSH. Then, via the top-of-rack switch, the experimenter can log into the FD compute node, which controls the full-duplex radios and runs the experiments. In this way, the full-duplex radios and example experiments are openly and remotely accessible to researchers, meeting a key goal of the COSMOS testbed. Next, we can watch how to log into the Sandbox 2 console and into the full-duplex compute node. So once in the terminal, we can log into the Sandbox'2 console over SSH, making sure to enable X11 forwarding. And once we're in, we can then log in again over SSH to the FullDuplex compute node. We can enter the password that is provided on the tutorial page, and then we are logged in. We can check what's available to us, and we notice this folder called FullDuplex Examples. Once we enter that directory, we can open up GNU Radio with the following command. Now we can have a look at the first experiment, which is real-time digital self-interference cancellation. To demonstrate and provide examples of our FullDuplex radios, we developed a series of experiments in GNU Radio. These experiments utilize custom C++ out-of-tree modules, which allow for real-time performance. These modules include digital self-interference cancellation and a module for programming the canceller PCB through the sub-20 USB to SPI interface. An example flow graph with custom blocks highlighted is shown at the bottom of the slide. So once GNU Radio is open, we can go to File, Open, and we can open up our node-level self-interference cancellation flow graph. Once it shows up, as seen here, we can press the green play button, and after a short wait, the GUI will open up. The first thing that we can see here is the time domain received signal. This is shown both after RF self-interference cancellation and after RF and digital self-interference cancellation. We can also see the same signals, but in the frequency domain. This shows the digital self-interference canceller taps, and if we zoom in, we can get a closer look. We also show the SI channel as estimated by the radio and the PC. Shown down here is the GUI used to configure the canceller PCB. Each of these sliders corresponds to a particular component on the board. This one here corresponds to the phase shifter of FDE tap 1. So if I move this, we can see that the board is responding in real time and we are seeing a change in the received signal. We will now demonstrate the second experiment, which is a FullDuplex OFDM packet link between the two radios. This is the OFDM FullDuplex packet link flow graph. We can see here that there are two OFDM packet streams that are being transmitted, and on the receiver side, there are also two OFDM packet streams, each of which also undergoes digital self-interference cancellation. The GUI that comes up shows us the following. These two waveforms represent the data that's being sent and received at each radio. One radio is sending packets that have data 44440000, and the other one is sending data that has value 01234, 3210, and so on. This is simply to differentiate between the two radios. We can see here that the radios are successfully receiving and decoding each other's packets while they are transmitting their own. We can see that by the sequence number increasing. We can also see the received signal spectra at each radio, and like before, there is the digital self-interference canceller taps. And when we zoom in, we can see them in slightly more detail. Now we will have a look at the third and final experiment, the packet reception ratio of a FullDuplex link. When we open the packet reception ratio flow graph, this is what we see. It's similar to the link experiment, except it has extra blocks for computing the packet reception ratio and the signal-to-noise ratio. We can hit play, and after a small wait, the GUI will open up. At the top here, we see the same time domain figure showing the received signal after RF self-interference cancellation and after RF and digital self-interference cancellation. We can also see the measured signal-to-noise ratio for each packet, the current running average of the packet reception ratio, and a slider here that lets us change the transmit power such that the signal-to-noise ratio changes. If we lower the signal-to-noise ratio, we can also see the running average packet reception ratio change in response, and the constellation diagrams become less clear. In conclusion, we have integrated two FullDuplex radios in the COSMOS Testbed. These radios are openly and remotely accessible to researchers and are available alongside example experiments. Researchers can use the integrated FullDuplex radios and example experiments in their own research. In the future, we plan to integrate more FullDuplex radios in Sandbox'2, as well as connect them to more powerful software-defined radios and compute nodes. The tutorials and open source hardware and software that we've been using can be found at the following links. Thank you very much for your time and for your audience today.